This worksheet is the collisions worksheet that we have. You can see the answers I have here. For these graphs, basically, I had to choose. It didn't say anything as far as which mass was or how much each mass was, but it did say that the dart had a smaller mass than the larger mass. I went ahead, just for the sake of the graphs, just said that the large mass was twice as much as the small mass, just so I can fill in and be able to get the boxes here. All right, so it says the three cases here. Case one, the dart embeds itself in the cart, so they stick together when they go through. That's why there's only one final on this one. Case two, the dart bounces backward off the cart, and then case three, the dart passes through the cart. All right, so initially the cart is at rest, so we have an initial momentum of 0 for all of these. And then for the dart, I just basically had to make up something as far as the mass, but I want the mass to be smaller, so I just made it 2, and then I started with 6 for the velocity. Now there's no real numbers here, so your charts may be a little bit different, but the consistency going across here should all be the same. So for each one, I set it as 12 just being the number of blocks I enclosed when I did 6 by 2, or 2 by 6, 2 by 6, and 2 by 6. Same thing with the initials all being 0 for the carts. Now afterwards, the final momentum has to be equal to the initial momentum, which is what conservation momentum says. So for this one, since I made the second mass twice as much as the third mass, or the first mass, then that means that with 2 here, that means when it embeds itself and they go off together, then that means the total is going to be 6 for the mass. And in order to have the same momentum or the same area, then that means that the height would have to be 2. So the speed is going to be 2. So 2 plus 4 blocks, and that gives me a total of the mass, and then times 2, and that will give me 12 here. All right, so for the second case where it says it bounces backward, I had to come up with some velocity backward. So I just said -2 for that. So that gives me a total of 2 for the dart for the mass, and then -2, and that gives me a total of -4. And then with positive 12 being the initial, and then the dart having a -4, that means in order to have 12 after, then this would have to be 16. So with this being twice as much, the mass being twice as much for the cart, then that means it's going to be 4. And then since it's 16, that means the height would have to be 4 here. So it's 4 times 4, and that would give me 16. The last one here, it says that I still have the same initial momentum for the dart and the cart. I went ahead and said that for the dart, it had a final velocity as it passed through, so it still has a positive velocity after. I said it has 2, and then that means for the other one here, for the cart, it would have to have a total of 8, and since its mass was 4, it would have to have a final velocity of 2. Now you may notice here, this is actually an issue. This is a problem. This last one here that I did is incorrect, and the reason I wanted to show you this was because I wrote it in pen, and I should have written it in pencil, because what we have is we have the final velocity of both the cart and the dart as 2 meters per second, which is actually what it was when they stuck together. So technically this is not correct, because this is not having the dart going through the cart. It would have to go faster than the cart. So I redid it. And so with the redoing it, I said, well, maybe instead of 2, I made it 3. So with 3, then that gives me 6 here, which means it has to be 6 here. And if the mass is 4, then that means the speed would have to be 1.5. All right, so I get my consistency here, where I've got the darts and the cart's initial momentum is 12, and the final momentum is going to be 12 as well. Over on the back, it asks to create mathematical representations. So basically, we're essentially making up numbers. So I start with the initial momentum for each one of those being 12, as you can see when I did it on the front. And I went ahead and went with the masses, 2 for the dart and then 4 for the large mass. So then I did my final velocities as well. And you can see that this, for the case 2, where it bounces back, that's going to be -2, so that gives me -4. And then we add that to the other side, and we get 16. And then we divide by 4, we get 4 meters per second for the bouncing backwards. For the one where they stuck together, or where it embedded itself, I basically treated the final momentum as just one object. So the 2 masses together were added together, and then we divide by the total and get 2 there. And then for the cases here, where again, the same initial momentum, but the final momentum where it went through it, so that means it went a little bit slower than it did initially. So it went from 6 to 3, but then that gave the final velocity for the cart to be 1.5. All right, so looking at these, it's pretty straightforward on which velocity is greater. And then this one asks which one's going to go up the incline further. So part of this, the irony of it is, I don't know if you noticed this, but we talked about how you're going to see a ballistics pendulum, but they're going to hide it. So this question is actually a ballistics pendulum, but it's hidden. And the reason why it's hidden is because you have change in momentum here, but then as the two go up together, you're going to have change in energy. And that those two conservation principles that we have in physics are used in this same problem. So the reason why it talks about how far up the incline is it's looking for height using conservation of energy. All right, so I said here the least change in momentum for the dart will have the least change in momentum for the cart. Bouncing backward has the biggest change in momentum, which means that it has the biggest velocity for the cart, as well as the biggest kinetic energy, the biggest final gravitational potential energy, and finally, it's going to have the greatest height. So bouncing back, which is this case right here, will always have the biggest change in momentum. And because it always has the biggest change in momentum, it'll cause it to go up the highest. All right. And then the dart that slows, that's slowing while passing through, so it still moves through, but it's only slowing down. That's going to be the smallest change in momentum, the smallest kinetic energy, the smallest gravitational potential energy, and therefore the smallest height by the time it gets to the end.